Okay, this video is about second lab, Picoscope. Okay, it's a lab sheet for this 3D1 class. Again, it's called second lab. And I need to apologize, first of all the Picoscope stuff, software, it's all PC driven, it's not Mac compatible. So I'm sorry, nothing I can do about that. But once you get to picotech.com, come over here and do their downloads, and you can do their software. Software is free, and it shows up over here. Okay, you can download it on your PC. This way you can view all the folders and saved waveforms. I'm going to go view. So I'm just going to go ahead and close this out. And what I've pulled up here is a thumb drive. I've got two little thumb drives I want you to put on your PC as well. I've got some files to get started getting better at the Picoscope. Sprat 1, the other thumb drive is Sprat 2. I keep them here right by my screen, right here at the base of it. Okay, in this folder I've got 381 Pico folder, first exercises folder, TDC. You need to download or click and drag this folder onto your desktop, because that is a great little software. We'll show you how that works later. We'll open that up as we go. But for starters, let's do this. Let's go into first exercises as it's labeled. Let's go grab a Pico waveform. And I'm going to go ahead and grab cylinder 1 at idle, good. Okay. And let's get started. Okay, there we go. Now this looks kind of like a big mess right now, doesn't it? Okay, let's move back out just a little. Whoops, wrong way. I want you to see where I go with my cursor or my mouse. Okay, right up here, the ×1. Well, let's go ahead and hit. Well, let's look at this first. The compression pressures of the cylinder are nice, all the same height. If I saw some variations in these spikes, I might think to myself, is my valve closing correctly? Or is a valve on that cylinder closing correctly? Let's go ahead though and go ahead and blow this up. ×4 ×8. Here's ×16. Okay. Let's get familiar more with this pattern. And the best way to get familiar with that pattern is to use some cursors. I think I'm ready finally. Okay, meaning on the far left of the screen it's in PSI, because we went in the Picoscope and we actually selected in-cylinder pressure test. You'll find that under automotive. But my point is this. Right here is 0. If you can see that. Yeah, we should be able to. This is 0. Here's 12.5 psi, 25 psi, etc. This cursor I'm going to put right here at the peak, and according to this, we're sitting here, and this is at idle. Spark plugs out of the cylinder, obviously. 90 psi. Now let's look at another aspect of this waveform. I'm going to drag it down to the 0 line. Because really, this is what's going on inside the exhaust manifold. We got just a little above or maybe slightly below. It kind of varies. Pulses, little tiny pulses of exhaust pressure. But down here, we're into a vacuum. Let's grab another cursor. I'm going to grab this, drag it down to about where it bottoms out. Right here, at the bottom of the trough. We'll call it the trough. And according to my little window up here, you can't see that probably, but it's 11 psi. Well, this is in a vacuum. And pressure and vacuum have a 2-to-1 ratio or relationship. What I'm trying to say is this is about 22 inches of vacuum. So let's follow what's going on here. The piston is coming up, okay, and it's a nice, symmetrical pressure build. And we have a nice symmetrical depressurization. And the exhaust valve, after combustion, has not, if we had combustion, of course the spark plugs out of this hole, but we can tell some condition of the cylinder, and more importantly, what's going on with the valves, because valves, finding a burnt and a poorly seating exhaust valve is kind of a challenge. You can do a compression test sometimes, and it looks fine with a compression test, but this test will help us find it better. Anyway, we're pulling into a vacuum until the exhaust valve opens. It starts to open. It just starts to crack open. Right here, we start to gain little pressure. The exhaust valve opens. We're starting to expose or let some positive pressure into the cylinder, and by this point, somewhere over in here, the exhaust valve is probably wide open. And so we got exhaust pressure, and what we don't see here is the stroke of the piston coming up here in the middle. In fact, let's just find out exactly where top dead exhaust stroke would be. I'm going to grab a cursor. I'm going to come over to here. And I'm going to put it on that peak. I'm going to grab another cursor and come over and put it on that peak. And according to this, look down in the right hand corner. It says 473 RPM. Well, we don't have the top dead exhaust stroke one here, so we got to double this RPM value. So it's 800 well, actually 940. Yeah, it'd be 946 RPM or something. But well, if I just use these numbers, 473. Let's cut that in half. I'm going to drag this cursor and find out where bottom dead center would be. Okay, 473. Hey, there's my RPMs getting higher. 982. That's about as close as I can get. Here's about where top dead exhaust stroke would be, but again, the valve is open. We can't see the pressurizing in the cylinder. So there's my 984 RPM. You can check engine RPM. You want to know what's going on or how fast the engine's going. So we're at 90. We reached 90 psi on the compression stroke. We've hit about 21 or 2 inches of vacuum. And right here we're showing very little exhaust back pressure. If I had a plugged exhaust, this would be above 0. In fact, anytime it gets above 2 or 3 psi, we got a restricted exhaust. This is a great way to look for plug cat. Engine's running, especially if you take it up to say 2500 RPM. We'll show you a 2500 RPM pattern here in a bit. It's a little different. Okay, so there's some cursors. How to maybe calculate or measure what engine RPM is, and of course pressure and vacuum. Okay, and I'll just bet you the intake valve probably starts to open somewhere right here. That's why we're starting to crack open, and by the time we get down to here, it's well open. Of course, the piston's coming down too. The piston's coming down here, isn't it? If we could draw a line here on the intake stroke, okay, between the valve opening and the piston coming down, we've got a good vacuum. And about right in here is probably where the intake valve closes, and now the piston continues on its travel in a sealed chamber to build peak pressure for the next cycle. All right, let's go grab another folder or another file. In fact, let's look at cylinder 1, 2000 RPM. Again, I'm going to blow this up. Let's zero in. Let's drill down. I'm up here on the, times 4, times 8, times, 16? I'm going to go back to 6. Well, let's go back to 16. Minimize this little guy. Looks a little differently, doesn't it? In fact, I'm going to grab my cursor. We'll drag it down at 2500 RPM. I'm building about 98 psi. Of course, the piston's moving faster. My exhaust, look at my exhaust pressure, still pretty close to 0, a little over, not much over, but we see some pulses a little above 0. Okay, and of course everything's happening faster. Okay, so now let's go ahead and talk about overlays. I'm going to pull the TDC software. I'm going to let it open up here, if I can get it to open. There it is. And you'll see it comes up, and we'll let it load. Now, all I want to do is turn on some overlays. We could actually come in and put down some degrees of events and other things and calculate valve timing and such. But we're just going to click on this little display TDC graphic toolbar. Calculate. Let's get this out of the way. Let's show you what this is all about. So I'm going to turn an overlay on, and look what appears. I can put that peak with this 0 degree indicator, 720 degree event, cycle event. We'll slide that there to the other peak. I'm going to drag this down. So we can now see we got, we got to readjust it. It always changes a little on. You got to change it back and forth a few times. Okay, 0, 180 degrees. We're at bottom dead center now. Here's where the exhaust valve just starts to open. And then top dead exhaust stroke, of course there's no peak here of pressure because the valves are open, especially the exhaust valve. That's where a peak would be for top dead center exhaust, but once again, there's no pressure in the cylinder, the exhaust valve's open. Somewhere in this region is where the intake valve opens because we start being exposed back to the vacuum. Of course, the piston, if we're to follow a ramp, the piston's moving down, the intake valve is moving open, and of course this will be like bottom dead center after the intake stroke. The intake valve probably closes right here, and we start to build pressure again for a nice building of pressure for the next event. Well, look what else I can do with my overlays. So I already got this one on. I'm gonna hit custom, and it doesn't matter which custom. I'll hit A, and I'll drag this over. Over in this corner it says pick, and it doesn't automatically load sometimes, so I gotta go find that folder. Let me think here. Where have I got that hidden? Just got to find my TDC software folder. So let's go into Pico. Whoops. Where have I got that folder? Here we go. In the actual software folder, overlays. And I like this red compression 3.b or bitmap, 3 bitmap, if that's what it's called. And I now have degrees, and I can overlay this. I'm just going to clear this one out, and let's use this overlay instead. Because now I understand how the degrees are. I'm going to go peak to peak, and I'm going to drag this down. So now, whoops, slightly slid it off. Drag it down just a little bit so I can just explain more. Every one of these red little hash lines is 30 degrees. 30, 60, 90, 120, 150, 180. Here is where bottom dead center would be. We like to see the exhaust valve open somewhere really close to 30 degrees before bottom dead center. We also like to see an intake valve. Look at here's where peak exhaust would be. The intake valve needs to happen pretty close within 30 degrees of top dead center exhaust stroke. And of course, as the intake valve opens, and the piston's moving down. Okay, imagine the piston moving down, the intake valve's open, we're building back into vacuum. Intake valve must close pretty close to here, Because as it closes, the piston obviously is moving up, building pressure for the next event. Okay, that's the overlays. And here's where much of the diagnostics occur. A shortcut, well, why couldn't you get a picture of a known good cylinder and maybe use your snipping tool for that, right? Where's all my, here we go. Here's all my programs. And let's go to accessories and snipping tool. And why couldn't I like snip? Whoops. What happened to my snipping tool? Okay. Whatever. Why couldn't I snip that? Go and compare it to another cylinder and really compare those two cylinders close to each other. Looking at this region especially, and this region, the opening and closing of valve events. Also looking at how much pressure was developed. Those are the three areas we're going to focus on. We're trying to diagnose compression waveform analysis. Let's see. Let's go look at, here's a Tahoe with a misfire. Guess I better click it harder. Wow, let's blow this up. Let's blow this up. There's some things to learn here. You probably recognize, let me minimize that. You probably recognize the compression waveform already now. Okay? This red line, I've synced it to ignition. And if you'll notice, it fires a little before. You zero in. Ignition fires a little before top dead center. Well, I hope so. Not only that, we've also synced into the fuel injector. Here's where the fuel injector fires. It's firing a little before an intake valve opens. So if I come over to here and come straight up, the injector fires a little before the intake valve opens. You can look to see if ignition timing and injector timing look like they should. This is a good pattern. All right, I'm going to go grab one more file. Let's go grab one more. The Malibu. Now, this car has valve, timing, camshaft phasers. And you're going to notice there's a little bit different look over here. It's a little different looking. A lot of things we've said before all apply to probably a solid camshaft, not a variable valve timing camshaft. So you are going to see differences in different vehicles. And we'll probably have to get used to these kinds of patterns and start understanding what's normal for each engine individually. But again, compare a good cylinder to a known bad cylinder, and it will work out. Let's see. I mean, look at the firing here. Of course, this is at 3,400 RPM. And I'll go back up to times 64. Ignition fires before top dead center. In fact, it's even more off center. It's even happening earlier. I can't change my scale. That's the picture it took. I'm just scrolling my mouse, doing my times. That's not too controlled. You can see ignition fires earlier at this RPM. Well, there's an introduction to Picoscope. I hope this has been helpful. In this folder, there's also the CarQuest book that talks a lot about pressure analysis. It starts going through here, and let's just go a little bit further, and we start talking about the actual what do you want to call it, the nuts and bolts of cylinder waveform analysis. It's a great book. Good luck. Okay, this segment of our video is going to talk about the pressure cylinder waveform kit from Pico. All right, in this kit, and this is about a $700 or $800 kit, we have our pressure transducer. Please don't drop this. But you do turn it on once it gets all hooked up in the cylinder. You'll hook your scope up here. Your lead from the spark plug hole will connect here. Okay, I'll set that there. This, of course, goes down inside the cylinder. Take the spark plug out, and this lead hooks up to our pressure transducer right here. This is for measuring fluid. You can actually measure fluid pressures if you'd like. But here's pressure. And again, it has a power button when you get hooked up. There is a fire wire, so it goes to a USB port, keeps this powered. Still have your channel and a little fire wire, both hooked up electrically to the scope. There's different fittings on here you can remove if you need a longer thread for your spark plug hole. And please anti-seize the thread. There's a little bit of anti-seize on here left over. Sure makes it coming in and out of the hole a lot easier. This silver braided piece is actually for hooking onto fuel pressure ports. And we can actually hook up to and measure the pulses, the pressure pulses in a fuel injector rail. Okay, that's an intro to the release of the kit. Okay, now let's go ahead and get a voltage pattern and current ramp and ignition coil. Now, the reason I chose these wires is, once again, this ignition coil has a purple wire, and it looks like, what, a green wire. This ignition coil's got a purple colored wire and a white wire. And this ignition coil's got a purple wire and a brown wire. So purple's got to be power from the ignition switch. Whereas the white wire, the brown wire, or this, whichever color this was, a green one, that's got to be your control circuit from the PCM. And again, I'm going to current ramp the power wire from the battery, and I'm going to voltage check the signal wire. Every ignition system triggers or turns on and off, turns the negative side on and off. Let's come over here and we'll do the same thing. Oh, one detail. If I'm going to mess with higher voltages, because ignition system, channel A here, which is back probed to the negative side of the coil and plug. Anytime you're above 40 or 50 volts, you're supposed to attenuate. So here's a 20-to-1 attenuator. I'm sure the voltage that I'm sensing is going to be in the 150 to 300 volt range. Guess we'll find out when we turn the scope on here. So let me go ahead and start it up. Okay, how did I get to where I'm at? That is the question. How did I get here? I got a nice looking, what we call a primary pattern on the ignition side. All of a sudden we fire the injector, we charge the coil, and we fire the the spark plug. And the duration, let's get some cursors, and well, first of all, how do we get here? Back again to automotive ignition. Let's go to coil and plug. We got lots of things to choose from. I'm gonna go down to primary voltage and current, and this is a 2-wire coil. Some have 3 and some have 4. GM likes the 4-wire coils, and there's reasons for that, but let's continue on this forward. So here's my voltages, and of course we're going to bring up my little sample. And my example looks pretty close to that. Let's go ahead and actually run And I'm going to slide this up. In fact, how many volts are we at? I'm going to bring a cursor. Cursor says peak of that primary ignition pattern is 330 volts. Not uncommon for primary side to see that. Now mostly it's 12 or 13 volt, 14 volts. But when we fire the plug, the coil, windings collapse, we induce a high spike of voltage, and then we actually burn. This is our burn time for our spark plug. Let's get some cursors and let's go see how long of a burn time we got. Average it about there, I guess. Get another cursor, drag it over here. Here's where the burn time actually starts. And according to this is given an RPM. Got a way to convert that to milliseconds. Oh, it's over here. It says 11. I'm not scoping that right. Nonetheless, I'm going to go ahead and change something here. I'm going to activate filtering. You can over filter, look at that. I'm going to get rid of the filtering in this case. Look how high the spike is, it's terrible. I'm just going to get the filtering back off. There we go. Get the cursors out of the way. Let's talk about ramp or current. Slide this up. Looks like the coil is drawing approximately, get this on a 0 here, I can get a real viewing. Current comes across, it's drawing about, well, -1, 0, so what's that, 2, 3, 4 amps, a little over 4 amps. And this coil, a normal one, looks like it doesn't peak out or levels off. It just keeps building until we fire the spark plug. But this is ramping and voltage pattern check for a coil on plug. Often a weak coil won't build normal current. What's normal? Well, it depends on the manufacturer, but normal is typically somewhere between 4 to 8 amps. Okay, let's talk about current ramping a fuel injector. Here's the ignition coils for coil on plug. Maybe we'll view those later. But I want to get a voltage and a current ramp pattern on this fuel injector. Okay, to set up, I've got channel A. Now I know this is the negative side of the injector because the positive side, each of these 3 injectors on this V6 Ford 3.5 liter non-turbo Expedition, 2014 Expedition. Each of these injectors have a blue wire, and the blue wire to each injector, fuel injector, has got to be from the ignition switch. Now each injector is a different color wire for the negative side that goes to the driver inside the PCM. This one's got a yellow wire. This one has like a brown wire, and this one over here has a green wire. Well, I'm going to back probe the negative side of the injector. I want to watch how it fires. The PCM controls the ground side. Back probe that, good. At the same time, on channel B, I'm going to use this current probe, just a low amp current probe. But I'm going to current probe the positive wire, the one from the ignition switch, not the one that goes to the PCM. We're going to watch the current flow and the negative side voltage. So we're going to current ramp and voltage this fuel injector. Okay. So, over here to the Picoscope. Let's see how I manipulate this. Get this to cooperate a little better. Okay. So, Now this is direct injected, so the voltage values are not going to be saved. But I'm still going to select automotive, come down to actuators. A fuel injector is definitely an actuator. Going to come in here to fuel injector petrol or gasoline. Let's go down here to multi-point injection. That means an injector for each cylinder. Voltage versus current. And this is what Pico is going to give me. I'm going to close the window, and here's a sample. Okay. Here's the current. It comes up. This is where the pintle actually physically opens and starts to spray fuel. Though the signal was actually, given here. Here's the voltage down spike. The voltage completing the circuit. The transistor closing. Okay, so the current starts to build inside the injector, and then the pintle is a magnetic change or influx, and so it actually opens the pintle when we spray fuel until we turn the injector off. Here's the voltage signal that got turned off. Here's the evidence of current being shut down. Okay, well, let's set this one up. Okay, I'm going to hit running. You know how to do that over there, or hit the space bar. I think I'm going to filter. Let's get some filtering going on. And the current ramp one, I guess I could filter it too. We'll get up to that 1 megahertz. I'm not even sure what, or kilohertz, 2 or 3 kilohertz, something like that. Not even sure exactly what that means, but it sure makes a nice crisp line. Here's my trigger. I got to have it just high enough. Well, you'll see why. Let's start this up, and you'll see how it's off scale. This is set up for a 12-volt system. Direct injection injectors operate on a much higher voltage. I've got to come over here and select maybe about 1 kV per division. Getting close to the scale, so let's go to 2 kilovolts per division. I've got the exactly what I'm looking for. Okay, I'm going to slide this up a little bit. There's my 0. There we go. Okay. Current ramp, look at that. I almost filtered, or if I filtered too much, I'm going to back off on the filtering. Well, didn't really change it. But nonetheless, you can see the current. It comes up. Wow, the pintle doesn't actually move till here, according to this one. Okay, here's our current ramp and voltage. The voltage pattern for a fuel injector for diagnosis. Filtering's really going crazy. Let me filter the other direction. There we go. There we go. That looks normal. I'm going to filter the other direction. Let's go 5 kilohertz. Alrighty. That's more what I'm looking for. Again, for a fuel injector voltage pattern, again, the switch is closed. In fact, I'm going to do something. I'm going to go put it in gear and give it some throttle, and you watch what happens to the pulse width of this injector pattern.